Hi, I'm Gamal El Dien, working as a research associate at Curtin University. Today I will talk about my recent publication about the start of global plate tectonic. Title: Mantle refertilization from 3.2 billion years ago pointed to an early start of plate tectonic. This work is already published in Scientific Report a few months ago. First, let's imagine the Earth's shape at 4.5 GA. This is exactly maybe the shape of the Earth with no plate tectonic, and in right hand side we see another figure for Earth today with different and several plate tectonic separated with each other. But how the Earth is transformed from its beginning and until now. Here's some figures describing the process simply. We first have the magma ocean, and around 4.4 the core started to formation, and we started to have a primitive mantle. After that we started to see some evidence about some proto-continental crust that exactly we know from Jacques Hill's zircon, and this proto-crust may be form Hadean depleted mantle. And the number C, we see the present today geodynamic and structure of the Earth with lithosphere, a continental lithosphere, and upper mantle, lower mantle, and core. So the chemical differentiation of the Earth from homogeneous cosmic composition into core and the mantle give us some of the plate. But when plate tectonic start and the subduction start, there are some studies, several studies about the start of plate tectonic. Some of them discuss about the start of plate tectonic around the Hadean 4.2, and other researchers and also discuss about the start of plate tectonic late for Proterozoic, around new Proterozoic, like Stern. But the problem or main problem in this work, all this work mainly discuss crustal geochemical proxy like zircon, and some of this work, even its work in the mantle, have preservation and geological base, and the little work let's give attention to the mantle itself. The mantle itself have two products: residual peridotite and direct melt product like basaltic and commodity rocks. As we know, for the early Earth 2 billion years in the early Earth, for Archean and Proterozoic, residual peridotite is few and not preserved. So the only composition we can study that basaltic and the commodity rocks. As I'm just say, when the Earth started to form and the crystallization of the core and the crust, we will find the sum of fluid mobile element and the incompatible element going to the crust like continental crust, and the gloss like subducted sediment, and at the same time the mirror of it, we will find depleted mantle in this same element. So what happens if this crust and sediment back to the mantle again? It will make a re-enrichment for the mantle, because mantle is already depleted in this element. So to study this enrichment, we can track the upper mantle composition through basaltic rocks, or we can discuss the lower mantle composition through commodity rocks, because commodity is mainly coming from the lower mantle. What we already did, we started to use some geochemical proxy like tracking some ratios like barium lanthanum ratios, barium niobium ratios, uranium niobium ratio, because this ratios is similar in compatibility but with very distinct chemical behavior, and this ratio is not affected by metamorphism and alteration, and also not affected during the partial melting. So in this case, if we track these ratios, we will track re-enrichment of the magma product. Also, we use neodymium isotopes. As we know, when as the Earth started to differentiate, the continental crust have small ratio from samarium neodymium, and the depleted mantle have samarium neodymium ratios more higher than continental crust. The continental crust mainly enriched in lighter earth element, but the mantle depleted in lighter earth element. If we see here in the left hand side the figure for neodymium isotopes mainly expressed as epsilon neodymium. This is the ratio between the neodymium isotopes in the source and in the rocks we have, and the chondritic rocks, we found mainly the mantle evolve in positive direction and the crust evolve in negative direction. So in this case, if we see some enrichment, meaning we going to the negative direction, this meaning we have some crustal contribution to the source of the study. What we already did, we collect all the database from basaltic rocks and ultramafic rocks as a comatite during the Archean and the Proterozoic from all the cratons, and all this craton is already representative for global and the time representative. As we see here, basaltic rocks and the comatic rocks is all representative for certain time in all the cratons during from 4 to 2 GA. What we exactly did, and we found in result for this figure, we found at around after 3.2 and 3 GA, we found there are major change in epsilon neodymium composition is going to the negative direction. This is meaning we started to have some recycling from continental crustal material. At the same time, we're tracking some ratios like barium lanthanum and uranium niobium in basaltic and the comatic rocks. We found the same significant change around 3.3 in basaltic rocks, and in comatic rocks around 3.1. To explain this significant change, we have two options. First option may be contamination of this magma during the ascending in the crustal material, or this enrichment may come from subduction or delamination. To eliminate the first evidence or first possibility, we compare thorium terbium ratio, because this ratio is already affected by crustal contamination with our ratio we already used in our work. For here from basaltic data, and here the comatic data, we compared with TTG, because TTG is the main continental crust. At this time, we found there are no overlap between our data and for basaltic data and documentic data and TTG. Also using this figure from Perth 2008, which exactly give you some indication about if you have the crustal contamination with your magma and your rock or not. We found our basaltic data and documentic data is mainly have the same trend and the parallel trend to modern Archean modern arc basalt, which already come from enriched mantle. So in this case, we eliminated the first option that this magma may become from contamination with when it is already placed in the continental crust. For the second evidence, so we have two options now. The first option may be this enrichment come from subduction or delamination, but according to Bitrat 2018 model, we found that delamination is mainly happening for oceanic crust, and oceanic crust is mainly coming from depleted mantle, and it will be depleted in this ratios we already tracking here in our study. And even if you have recycling these ratios, it will have less effect about the upper mantle. And also from the model we see in the right hand side, this recycle don't going to the lower mantle. This is not consistent with the figure we show from comatic rocks, what exactly tracking the lower mantle composition. The other option, it should be subduction, as we have some numerical modeling for Van Heuen and Moyan 2012. They already say that subducted slab can be going to the lower mantle. So as we say from comatic rocks, we found the comatic rocks, so the same pattern like basaltic rocks, they have enrichment around 3.2. Our data is also consistent with different work from us when we tracking some trace element and major elements that track the temperature of the mantle. We found there are major drop in the temperature, as the melting temperature around 3.2, and this is major drop may be result from subduction also. So we exactly say here that enrichment and of this mantle and exactly the lower mantle, as we say from comatic, the only option can do that, it will be the subduction. For our conclusion, during using some geochemical proxy like fluid mobile element ratio and dim isotopes for mafic and ultramafic magnetism, we display there are increase in magnitude and variability after 3.2, and we suggested that 3.2 represent the onset of a global enrichment and refertilization event, and also this enrichment may be come through recycling for crustal and the supracrustal material, including sediment and the crustal rock that back to the mantle again through subduction. And this is new observation give some hint that around 3.2 we have onset of global subduction process, and even this subduction also may be going to be the deep subduction, and this subduction process mainly should be happen through plate tectonic.